In today's lecture, we will look at time constraint scheduling. So, time constraint scheduling is the problem of allocating C steps to operations using a minimum number of resources given a latency constraint. So, we will be given that we must schedule, we must complete the scheduling within a given number of C steps, and within that given number of C steps, with that upper bound on the given number of C steps, I must try to minimize the amount of resources that I will use. So, this problem, like the resource constraint scheduling problem, is an NP complete problem and has a similar state space. So, before as we did for the resource constraint scheduling problem, we will look at the ILP model. So, the ILP model for the latency constraint scheduling problem is very similar to that of the resource constraint scheduling problem. The main difference being the objective here differs. So, what is the objective here? We want, given a bound on the time within which to schedule, I need to minimize the resource that is consumed, that means the area that is consumed by the circuit. I want to minimize the area that is consumed by the circuit given a limit on the time that I can use to schedule the operations in my DAG. So, how do we specify this objective? Minimize k equals to 1 to nr cost k into ak. So, if this is, what does this mean? Here cost k is the area cost for resource of type k, and ak denotes the number of resources of type k. So, what do we want to minimize here? We want to given the area that a certain resource, a certain functional unit will take, means I know before the scheduling for each type of resource, I am given the type of resources. Now, for each given type of resource, I know the total amount of area that is consumed by one instance of the resource, that is known to me. However, through scheduling, I need to find out how many resources of each type should I use, so that I will be able to schedule all the operations in my DAG in the given time constraint, and while minimizing the total resource consumed by, total area consumed by this set of resources. So, that is why for resource, suppose I have two resources, multiplier and adder, then let us say A1 is adder and A2 is multiplier, then cost 1 is the cost, area cost of the adder, and cost 2 is the area cost of the multiplier. So, an important thing to note here is that unlike the resource constraint scheduling problem, AK is not known. That means the number of resources of type K is not known. It is now an unknown auxiliary variable, and that has to be determined by appropriately scheduling the operations. Also, in this problem, we need a latency constraint, a specific latency constraint, and let us say that latency constraint given to us is lambda. Now, in the previous one, we also had an upper bound of the latency constraint lambda, but we wanted to minimize the time within which to schedule all operations given the number and types of resources. Here we also have a time constraint lambda, but here we want to minimize the resources, so that max within this lambda I can schedule all my operations. So, what do I want, what is the latency, how is the latency constraint specified? It is specified by saying that here it will, here I have written a bit wrong in the sense that this I variable will be n. So, what I want is that the nth variable, this whole expression tells me the start time of the nth operation, that means the sync node. I am saying that the sync node should be scheduled at most within lambda plus 1. So, for all the other nodes, sync node is a dummy node. So, for all the actual operations that I have, that must be scheduled within lambda, and the start time of the sync node should be less than or equal to lambda plus 1. So, here again I am telling that there is a mistake in the expression. Here I should be replaced by n, the sync node. So, what I want to say again, I want to specify that the start time of the sync node should be less than my time constraint plus 1. So, the overall ILP formulation for the time constraint scheduling problem becomes minimize the objective function such that the constraints that are specified. We will go through the constraints, just brush them up very quickly. The objective function again is what? Objective function attempts to minimize the total area of the circuit such that the operations can be scheduled within the time constraint lambda. Now, here the first constraint here specifies the unique start times of all nodes, as we have seen in the last lecture. This one, the second constraint gives me the dependency constraints. That means, if I have two nodes with edges, dependency or precedence constraint edges between them, then one must be scheduled after dj times the other has after dj times the other has started. So, the start time of the dependent operation should be dj times after dj amount of time the first operation, where dj is the delay or execution time of the first operation. Now, we also have resource constraints. We said that for each resource type at each time step, I can only use a maximum number of resources. I can only use a maximum number of AK resources of type K. So, that is how we specify resource constraints, but again here AK is not known and is an outcome of the scheduling problem. It is an auxiliary variable here. And then we specify the latency constraint, which is specified by the start time of the nth or the start time of the sync node, right. So, the sync node must start at most within lambda plus 1 time steps. Given this formulation, we will now take a small example. So, how does this formulation proceed? Given this operation constraints graph on the left, let us say we use the same time constraint lambda equals to 4. We know the solution, but we will go through the steps here while doing time constraint scheduling. So, we are given the operation constraints graph, and we are given the constraint on the time. We are also given the types of resources. So, for k equals to 1 ALU, I have a cost of 1. For k equals to 2 multiplier, I have a cost of 5. I have a cost of 5. So, what does it mean? It says that ALU has an area cost of 1 and multiplier has an area cost of 2. Here this is not cost 1 but cost 2. So, cost 2 is 5. That means, the multiplied unit, functional unit or resource consumes an area of 5 on the circuit, and the ALU, which is 1, k equals to 1, has a cost of 1, meaning that the ALU consumes an area of 1 on the circuit. Now, given this, we know that to schedule this, we need at least 2 ALUs and 2 multipliers from the resource constraint scheduling problem. So, this is what we did not go through, but this is what the ILP will exactly tell me. The time constraint scheduling ILP will also give me the same solution, that to schedule within 4 time steps, you need at least 2 ALUs and 2 multipliers, and that is the least cost solution that you have in terms of area required. So, what is the cost? So let us say if I require 2 ALUs and 2 multipliers, as I have said, the total cost will be the total multiplier cost plus the total ALU cost. So what will be the area cost, total area cost of the circuit? So 5 is the cost of one instance of the multiplier. I have two multipliers, so the total cost is 10, and 1 is the cost, area cost of the ALU. I have two ALUs, so 2 is the total ALU cost. So the total area cost of the circuit becomes 12. So with this understanding of the ILP solution, we now briefly see how the branch and bound solution differs for the time constraint scheduling problem with respect to the resource constraint scheduling problem. Now, in the time constraint scheduling problem, at any given state of the state space, what do we store? We store the maximum number of resources that I have consumed in steps 1 through I minus 1. So we take the same simplistic assumption that I have one type of resource, 3 instances of that type of resource, and everybody we are assuming has a delay of 1. So what will be the max resources? That means at each time step I will require some number of resources. Okay, here I need to minimize the number of resources is not given to me. Here I want to minimize the number of resources. Now, at any given state, I have started from the root and have come to this state. At any given state, the way in which the state space will be expanded will be a bit different here for the time constraint scheduling compared to the example that we took for the resource constraint scheduling. Why? Because here we will no more exhaustively allocate all resources. We will no more exactly allocate all resources to all the time steps. We want to minimize resources. Rather, the number of resources is not given to me. Our choices will be allocating each operation to a distinct resource. I may allocate an operation to a resource, I may not allocate an operation to a resource. And although the other things what we discussed for the branch and bound remains same, that I need, if all my operations at a particular time step gets exhausted, I need to increment time to get back any resource that I have. Right? So at any point in time, this branch and bound here will keep an account of the maximum number of resources that has been used in C steps 1 through I minus 1. Why? Because if that many resources have already been used from the initial state to the current state, that many resources will at least be required. Because we have already used in a certain time steps 3 resources in parallel, let us say. So 3 resources will be required in the solution. What is the solution? We again said a path from the root to the leaf in the state space tree is a solution, is an enumeration of that solution. So in that path, if the maximum number of resources that has been consumed at a time step is 3, there is no way that I can execute that I can produce a schedule with this path that consumes less than 3 resources. So the answer for this path will be 3 resources. So what is basically the answer in the time constraint scheduling problem? What is the maximum number of resources that has been used up in any time step in that particular solution from the root to the leaf, right? So that will give me a solution. Now n, at that state, n gives me the number of remaining unscheduled operations and t is the remaining number of C steps. Now for the resource constraint scheduling problem, we did not know, we wanted to minimize the number of C steps in which I want to schedule. Here I am given the number of C steps that I have. So I have currently already used a certain number of time steps, and I have a certain number of time steps within which to schedule my remaining operations. And my basic objective is to minimize the consumption of resources such that all my operations will actually be scheduled in those t remaining number of time steps starting from this state. So what is my pruning function here, Fn? My pruning function here, I will first start with a very crude pruning function. A very crude pruning function here would be that the maximum of r I minus 1, which means that the maximum of the number of resources that I have already used in any of the prior time steps between I equal to 1 to I equal to I minus 1. That means before the current time step, what is the maximum number of resources in any given time step that I have used, and a lower bound on the minimum number of resources that I may need to use at any given time step for the remaining time steps. So I have a remaining number of time steps. In any of these time steps, what is the lower bound of the maximum number of resources that I may need? Now a max of Ri minus 1 and ceil n by t. So ceil n by t, it gives me what? N is the remaining number of operations, t is the remaining number of time steps. So n by t is the minimum number of resources that I may need at any time step, given that I can use the maximum, there are no dependency constraints. Given that there are no dependency constraints, n by t is the minimum number of resources that I may need at all time steps for the remaining t time steps that I have. Now Ri minus 1 comma ceil n by t, max of this gives me the lower bound for my current state. So why do we use this Fn? We use this Fn to compare with the current best solution that I have. So I have already traversed through another path of the state space and have already found a current solution. Now we will compare at this state with the current solution. If the current solution, the current best solution tells me that it can schedule with a lower number of resources within the time bound, then my solution lower number of resources than the lower bound that is produced by at this state. So at this state, Fn gives me a lower bound of the minimum number of resources, lower bound of the number of resources that I will require at any time step. Now when I am comparing with the current best solution, what I am getting is that when is the current best solution be always better than the lower bound? When will it be? When the current best solution has a lower value. The current best solution will have a lower value, meaning that in that solution the maximum number of resources that I may require to use in parallel at any time step is lower than the minimum number of resources that I require for this solution. So at this state I can prune the rest of the subtree, which means that I do not need to explicitly expand the rest of the subtree and can look into other parts of the state space to find a better solution. Now ceil n by t is a crude solution. We can still use better and better solutions, but I leave it to the student. I leave it to the student to find these solutions, and we may discuss outside the scope of these lectures in the assignments.